All right, guys, are there any questions over the homework before we get started? Question over the previous assignments before we get started? No questions? Okay. All right. This is where we're starting today. Find a number that when multiplied by itself, you get a negative number. So, thank you. Now this, I don't think is on the first part of your note sheet, but this is the first thing I do want us to look at. Find a number that when multiplied by itself, you get a negative number. Well, let's just pick a number. Let's say 2 times 2 is 4. So positive 2 times positive 2 is 4. So that doesn't work because we want to get a negative number. Now if we said negative 2 times negative 2, we would get 4. And this is the issue that we have when multiplying a number by itself. There's no way to get a negative number. And that's the issue, especially if you remember one of the problems from Friday, where we talked about the square root method. We couldn't find the square root of negative 5/4 or 5/2. I think it was negative 5/2, because there is not a number when multiplied by itself that gives us a negative number. And if we think of it in a more simpler case, we're trying to say what times itself gives us negative 1. Because that's what it really boils down to. What times itself gives us negative 1? Well, we're going to imagine a number. I'm going to call it I. And what we're saying is that I squared is negative 1. When we multiply I by itself, we get negative 1. So if we want to figure out what I would be, well, the square root of I squared would be I, and it's equal to the square root of negative 1. We wouldn't consider the plus or minus case, but we get this here. And actually, this is what I is. I is the square root of negative 1. I believe some of y'all made the comment that the ACT had I like this here on it. This is what it is. I is the square root of negative 1. And we need it for quadratics to be able to solve. Because up to this point, any of the ones that we had that had no real solutions, I is involved. Because I is what we call an imaginary number. I is an imaginary number, and I believe I spelled imaginary right. Yeah. Imaginary is an imaginary number. Now, they are also considered to be part of complex numbers. And a complex number is where we have a real number and an imaginary part, which comes in the form of a plus bi. So the solutions to our problems that we had on Friday, the problem that we couldn't get the answer to, would actually had an I in it. So we could have found it, we just had to simplify with I. Now these three are the first three that we have. And we want to simplify them in terms of I, with I as a part of them. And if we look at the first one, the square root of negative 25, well, we're going to do it step by step, and then we can do these a little bit simpler, a little bit quicker once we get the hang of it. Because when we say the square root of negative 25, we're really saying the square root of negative 1 times 25. And according to the properties of radicals, we can break this up into the square root of negative 1 times the square root of 25. What's the square root of 25? 5. And what did we just say the square root of -1 is? I. Because the square root of -1 is I. So the square root of -25 is 5i. Questions on this here? It's not so much the letter I chose to use, it's the set. It's the one we're supposed to use. I is one of the few that doesn't get used for most solving equations, unless it's capital I, has a specific purpose. Lowercase I is normally avoided, especially when we've used X, we've used A, B, C. We've used almost every other letter, but we won't use I, because especially in Algebra 2, I is defined as the imaginary number, which is the square root of -1. The only other time I gets used is with vectors, and in those cases we use I and J to denote vectors. Now the 30xs, which we've seen already, is very useful with square roots. It can't find the square root of -25. It just won't do it. But what we do know with the square root of -25 is that we can simplify the 25. The negative is going to come out as I. So if we look at the next one, square root of -72, well, this is the same as saying -1 times the square root of 72. So we would have the I. Now we need to see if we can reduce the square root of 72. It's not a perfect square, and because the negative, the 30xs won't simplify it. But since we know the negative is going to come out as I can remove it and just have it do the square root of 72, which is 6 square roots of 2, yes? Now because our actual one is -72, again, the negative comes out as I, so we'd have 6i square roots of 2. Questions on this here? Now the question is, can the graphing calculator do these? And the answer is yes, but it has to be in A plus BI form. So if you see between auto and degrees, it does say A plus BI. It'll do those there. Now if it says real instead of A plus BI, if we click mode, so this is the mode, it's how it's set up. We're putting things in. If you notice about halfway down underneath sequential, we have real and A plus BI. If it's on real, we'll go down, move over one, hit enter for A plus BI. In A plus BI mode tells it we want it to calculate in terms of I, these complex numbers, these imaginary numbers. Now I believe the next one was -5 square root of -9. So other calculator, -5 second square root -9. Enter is -15i. Now if we did this by hand, we would have -5 times. Well, since we're taking the square root of -9, the negative would come out as I. It would come out as I. Now what's the square root of 9? 3. So the square root of -9 is 3i. We can multiply those two together. -5 times 3, -15. And that's it. Questions on this here? We have 4 more here. So the next one, square root of negative 4. So the negative from negative 4 would come out as I, leaving us with the square root of 4. And the square root of 4 is 2. So the square root of negative 4 is 2i. And the graphing calculator can do that there. Second square root of negative 4 is 2i. Now, we're taking the square root of negative 12. Second square root negative 12 is this here. Is 12 a perfect square? No. So, yes. 2 square roots of 3 is what it would be. Now, the graphing calculator is going to turn it into decimal form every single time, if it's not a perfect square. So if we think of the last 2 that we did before this, 9 is a perfect square, 4 is a perfect square. So it gave us nice numbers. Square root of 12 is not nice, but I do know the negative will come out as I, yes? Now the 30xs, the one that does reduce radicals, cannot handle negatives inside of a radical. But I know the negative is going to come out as I. So now I can put it in the other calculator as the square root of 12. So 2 square roots of 3, we plug it back in with I. So 2i square roots of 3. So we get how this works, yes? So some of them, especially, we say the next one, negative square root of negative 36. Square root of 36 is a perfect square. So if we want, we can say negative second square root negative 36 is negative 6i. That's it, because the square root of negative 36, the negative is our I, and from coming out of the radical, square root of 36 is 6, gives us 6i. The negative out front makes it negative 6i. 2 times, well, square root of negative 54, the negative is going to come out as I. 54 is not one of our perfect squares. Square root 54, 3 square root of 6. The square root of negative 54 would be 3i square roots of 6. Last thing we have to do is multiply it, giving us 6i square roots of 6. Questions on this here? Any questions on anything we've done so far? A little bit, not really, but a little bit. Powers of I. I is the square root of negative 1. I is the square root of negative 1. Now, you can follow along with this, or you can watch. Either one's going to work. I think it might be better to just kind of watch and see how this works. And if you do not fully grasp what's going on, it's fine. We're looking for patterns. I'm going to show you patterns, okay? Because we're talking about powers of I. We're talking about putting I to a power. Because I to the first is the square root of negative 1. That's just by definition. Now if I square it, so we'd have the square root of negative 1 squared. Well, the square root and square would cancel, telling us it is negative 1. I cubed. Now we can look at it as the square root of negative 1 cubed. Or really it's just I times I squared, because we have 3 of them. And the reason I use I squared is because we know what I squared is, yes? What is I squared? So we're saying that we have I times -1, which is negative I. Okay? I'm going to do this again. Let's do I to the 4th. Really, we just, all right, we can do I squared times I squared. Well, I squared is -1 in both cases. So we got that I squared -1, so it's really just I. We got that I squared is -1. I cubed is -I. And then we just got that I to the 4th is 1. Okay. And at this point, there is nothing that's been kind of really interesting. Let's keep going. I to the 5th. Well, that's the same as saying I to the 4th times I, yes? Well, what's I to the 4th? Which would be 1 times I, which is just I. Okay. I to the 6th. Well, you say that's I to the 4th times I squared, yes? Well, I to the 4th is I to the 4th is 1. I squared is -1. So we get -I. Okay? I know this is a little weird. I to the 7th. Well, that's just I to the 4th times I to the 3rd, yes? Well, I to the 4th is 1. I to the 3rd is -I. Y'all starting to see a pattern? I to the 8th. Anybody have a guess? We can say that's I to the 4th times I to the 4th, which would be so really I to the 5th is the same as just I to the 1st. I to the 6th was the same as our I squared. I to the 7th was the same as I to the 3rd, which was -I. And I to the 8th was the same as I to the 4th, which was 1. So no matter, we've gone through 8, and we could keep going through this, but there's only 4 things that keep showing up. We either have I, -1, -I, or 1. No matter what the power is with I, it's going to reduce to one of these 4. We cannot leave I to a power other than 1. So if we get I squared, I cubed, I to the 4th, we have to reduce it back to one of these 4 here. We got to reduce it back to one of these 4. Now to do this, for any I to the n, you take the value of n and divide it by 4. And it has it listed this here when the remainder is 0, or we get a number 0.00, or we get the number without a decimal, because when something divides by a number evenly, it's 0.00. In a calculator, we don't have a decimal number because it doesn't show it. It's going to reduce to 1. If we have a number 0.25, that power of I is going to reduce to I itself, because it's the first one in our sequence of 4, yes? Now when the remainder is 2, it says remainder 2, we have a number 0.50, we get -1. And if we get a number 0.75, we get negative I. And the way to think of this is because, again, I, negative 1, negative I, 1. We have 4 spots it could be, and we're switching between them. Really, our starting one is 0.25, 1/4, or I, 2, 3, 4, and it just repeats. Now, you might be fine with that there, and the n is just a number, because it could be 4.25. We really care about the decimal. We don't care about the number in front. The number in front is just telling us how many times through this cycle of 4 we went. It doesn't make any difference. Now, this will make more sense when we actually start evaluating. So if I want to evaluate I to the 27th, what we're going to do is I'm going to take 27, its power, and divide by 4. Because we have 4 different options for this here. It's going to either land on I, negative 1, negative I, or 1. So there's 4 choices it could be. The first, and it kind of goes in cycles, I, negative 1, negative I, 1. I, in that case, so I is the first, so 1, 4, negative 1 is the second, 2 fourths, negative I, 3 fourths, and 1 is 4 fourths. Now we can do 27 divided by 4, which gives us 6.75. Yes. Now we don't really care about the 6. 6 just tells us we went through all 4 possibilities 6 times. So we look at 0.75, which is negative I. Because I is 0.25. Negative 1 is 0.50. Negative I is 0.75. And 1 is 0.00. But for most calculators, unless they're set to round or go out to 2 decimal places every time, it won't give us 1 for 0.00. We're ready to look at the next one. 34, I to the 34th. Well, we can take 34 and divide by 4. 34 divided by 4 is 8.5. It'd be our 0.5, and 0.5 matches up to negative 1. So I to the 34th is negative 1. I to the 47th. We're going to take 47 and divide it by 4. The 0.75 tells us this will become negative I. I to the 65th. We take 65 divided by 4. And the last one, I to the 1040th. 1040. 260. Because in the calculator, it'll give you a flat 260, which the decimal is understood to be 0.00. So it's 1. Questions on this here? Second decimal. Graphing calculator does have I. Now, we do see the 1 part, yes? But it gave us this 4e to the negative 12i. I'm going to add this here, 4e to the negative 12i. What this is saying, e is just another way to say 10 to the number after it in the calculator's terminology. So it's saying 4 times 10 to the negative 12. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is what this number is saying. Now, for all case and purposes, this is 0. Because the calculator uses graphing to actually find these powers. And once we get to really big numbers, that 4e to the negative 12 is essentially the size of a pixel on the screen. So there's a pixel error that occurs for that one there. Now, I think let's just do 5 to the 16th is 1. 16 divided by 4 is 4.00. It is 1. So for small powers, the graphing calculator can do it just fine. It doesn't have a pixel error. But once we get to really big powers, it has a pixel error, and we have to interpret that. But questions on this here? All right, because I think we feel pretty comfortable with that, especially with our 0.25, 0.50, 0.75, 0.00. And again, I would highly suggest, especially on the review sheet, to have that written down somewhere so that you can reference back to it. Sum and difference of complex numbers. To add or subtract two complex numbers, add their real parts and their imaginary parts together separately. So a plus bi plus c plus di. But we'll add the a and c, b and d, and get our answer. Same with subtraction. So 8 minus I plus 5 plus 4i. So if we drop the parentheses because we have a plus in the middle, signs are not changing. So we have this here. Now 8 plus 5, our real parts, would be 13. Now our imaginary parts, negative 1 plus 4i. What do we think? 3i. Plus 3i. In a lot of ways, we can treat I like we would a variable x with addition, subtraction, multiplication, division. We can treat it like a variable in a lot of different ways. The only thing that changes is if I becomes to a power. As if we get I squared, I cubed, we do have to reduce it back to 1, negative 1i, negative I. But that's it. Questions on this here? Let's look at the next one. Now we do need to be careful because we will have to distribute this negative, which would give us negative 3 plus 6i. Our real parts, 7 minus 3 is 4. Since we're subtracting it, that negative has to be applied to it, because we're saying 7 minus 3, negative 6i minus negative 6i. Because really this has, we can consider almost negative 1 in front of it, and it has to be applied to both terms. We technically did apply the plus to both terms in the first one here. It's just that a positive 1 times 5 is still positive 5. Positive 1 times positive 4 is still positive 4. It doesn't change the sign. Questions on this here? Negative 6i plus 6i is almost negative 6 plus 6. 0. So this is actually just 4. Because, I mean, we could say plus 0i, but 0 times anything is 0. So we don't need to include 0i. It's just 4. Questions on this here? 13 minus 2, or 13 minus quantity 2 plus 7i in quantity plus 5. So we have 13 minus 2 minus 7i plus 5i. 13 minus 2 is 11. Negative 7i plus 5i is negative 2i. Questions on C. 2 plus 9i. Not what I wanted. 2 plus 9i. Was it plus minus I? Yes. Now it seems odd that the calculator will do these, but it won't do the others. It won't do any other expression simplifying it because, as I've said before, the variable has to have a value, yes? I actually does have a value. Its value is the square root of negative 1. It's not going to leave it as the square root of negative 1, and it can combine it. So we get this here. So that's the answer. Should be a parenthesis there. Yep. 13 plus 4i plus 4i minus unfortunately, the 30xs can't plug these in, but for these here, addition, subtraction, the graphing calculator will handle them just. So so if we did this one here, 16 minus, I just lost, 13 plus 6i, 13 plus 6, to get I, we go second decimal point. And then I lost the last piece of this one. Plus 8, and then second decimal to get I, enter, 3 plus 2i. I probably should have told you all to get your graphing calculator for this, but it still works. Yeah. Questions? Huh? You're on this one? So this one here, we're multiplying. So we're going to do, I'll do one by hand so that we can see this, because we're going to distribute the 4i. 4i times negative 6. 4 times negative 6 would be 24, and we do have I. 4i times I is going to be plus 4i squared. Now again, we can't leave I to an exponent other than 1. We do. What is I squared? It is negative 1, because we could do the 2 divided by 4, which would be 0.5, which is our negative 1. Out of all of them to know, I think I squared being negative 1 is a good one to kind of have off the top of your head, because it's the one that occurs most often. So we'd have negative 24i plus 4 times negative 1. Well, our 4 times negative 1 would be negative 4, and we get this here. Now, normally when we write it, we want the I term second and the term without I first. Our real parts goes first. Our terms with I goes second. There's normally just standard form for writing these. Questions on this here? Feel good with the first one? Now, if we look at the second one here, okay, 15I times negative 1 plus 2I. If I did this in a calculator, we can do 15I times negative 1 plus 2I. Negative 1 plus 2I. Oh, nope. Plus 2I, enter, negative 30 minus 15I. Because if we did this by hand, 15I times negative 1 would be negative 15I. 15 times 2 would be 30, and I times I would be I squared. Now I squared is indeed negative 1. And our positive 30 times negative 1 would be negative 30, and then our minus 15I. Questions on this here? We always want to write them in standard form. Standard form for any complex number comes in the form of A plus BI. We want to put the real part first, our imaginary part second. Yep. That's not technically wrong to put it as negative 15 minus 30. We normally write it the other way. Multiply these in standard form. As we've kind of seen already, the graphing calculator can do these. I'm going to do the first one by hand. 9 times negative 4 would be negative 36. 9 times 7I is going to be plus, not 54, 63. Because I was thinking of 6. 6 is 54, 7 is 63. Then we do the same thing with negative 2. Negative 2I times negative 4 will be plus 8I. And negative 2I times 7I is going to be negative 14I squared. Now we do need to do some simplification. 1 is going to be 63I plus 8I, which is 71I, minus, well, our I squared is negative 1. Well, negative 14 times negative 1 is plus 14. Now, I did move it over next to the negative 36, mainly because they are indeed like terms. And negative 36 plus 14 would be negative 22 plus 71i. Questions on this here? 9 minus 2i minus 2i. What is it? Negative 4 plus 7i. I think I know what I did wrong. Yep. So what I did wrong is I put a minus instead of a negative in front of the 4. Since I put a minus, the calculator is expecting a number or something to be in front of it other than a parentheses. So it threw a fit. But negative 22 plus 71i, is that what we got? Yeah. Four minus 12i, 11 plus 8i. 4 minus 12i times 11 plus 8i is 140 minus 100i. Questions on any of this here? It does seem like a lot of problems because the first set, 6 through 16 even, you're simplifying radicals or square roots in terms of I. 20 through 26, powers of I. So the first one's I to the 94th, reducing it to I, -1, -I, or 1. 31 through 34, addition, subtraction. 37, 39 is also addition, subtraction. And 43 through 46 is our multiplication. Yeah. Yeah. I think I was, because it is a good number of problems, and it was not going to add anything. Not as that it's not important, but having it and not having it would not have helped y'all better understand it. And y'all are already doing a good number of them to begin with.